Hello, everybody. All right, so here we go. This is the last topic before your first test. So, linear and absolute value inequalities. So, this stuff you should have already seen before, but we're just going to kind of go back over what we're going to go through. So, we're going to look at interval notation. We're going to find intersections of unions and intervals. Solve linear inequalities. Recognize inequalities with no solution or all real numbers as solutions. Solve compound inequalities, and then solve absolute value inequalities. So we actually have kind of a lot to do, so let's get started. Solving an inequality. So an inequality is the process of finding the set of numbers that makes the inequality a true statement. So that's the whole goal. We're going to make true inequality statements. These numbers are called the solutions of the inequality, and we say that they satisfy the inequality. The set of all solutions is called the solution set of the inequality. So when we are dealing with inequalities, we're going to be representing these in a couple of different ways. And so one of the way is through interval notation. And the other way that you're going to see it is going to be set builder notation. So set builder notation looks like this. And so we have x such that x is greater than 2. So we have the set of, so that's the brackets mean. So when you're looking, or the braces. So when you're looking at set builder notation, it's in this format. And then so the braces means we're looking at the set of, and then all x. So whatever variables right here, that is what we're actually going to wind up putting in there. So the set of, oops, didn't mean to do that. All x, and then that line means such that, and then what interval notation? So whatever the greater than or less than sign, or whatever you want to put here. So we can use set notation in other places besides inequalities. But whatever you put here, the restrictions will go right here. So that's what we want. So when you're looking at set builder notation, this is what we're going to be looking at. When we look at interval notation, we're looking at basically as either parentheses or brackets. And so we have what's called an open interval and a closed interval. Open intervals are always going to be represented by parentheses, whereas closed intervals here are going to be represented by the brackets. So again, open interval is parentheses and closed intervals are brackets. Anytime we deal with an infinity, infinity is always going to be a parenthesis. It will never, ever, ever be a bracket because we have no idea where the infinity is ever going to end. Because why? Because infinity doesn't end. And so when we're looking at this, we are looking at, you're going to start at some random number, for instance, and go all the way to infinity. So what this is saying is that we're starting at some random x value. That means x is going to be greater than wherever a value that you're going to be looking at. So that's how, when we're dealing with interval notation, we read it with the infinity sign. If it includes it, for instance, so see how this one has a bracket here? So we make sure that we use the greater than or less than, or greater than and equal to, or less than or equal to sign. And what that looks like, so this is going to be your interval notation, and then this will be your set builder notation here. Okay. So when we deal with interval notation, make sure when we talk about, just talked about this, parentheses indicate endpoints that are not included in an interval. Square brackets indicate endpoints that are included in the interval. And then parentheses are always used with an infinity or negative infinity. So that's just something you need to remember and that you need to understand when you're actually going through this whole entire process. So use interval notation express the interval in set builder notation and graphs. So when I'm looking at this in set builder notation, I've got, here's the interval in question. So they're asking me, this is my problem here. So I want to take this, and I'm going to take this, and I'm going to turn it into this. So what you need to look at is we're going to go from 1, and we're going to go all the way up to 3.5. So I know I'm going to start at a 1, and I'm going to end at 3.5. So since I have a start and a stop, I'm going to have something here in the middle. And since my 1 is going to be less than whatever's in the middle, that's why the 1 here, and I get a less than here. And I'm going to end at 3.5, so we have that. But now, because I have brackets, I've got the equals that I have to put up under each of these. So this is what it would look like in your set builder notation. So you'll take this piece of information here and plug this into your set builder notation, and then that's how these two are going to be related. In terms of graphing, you can do it with an open dot or a closed dot, or you can do it with a parenthesis or a bracket, your choice. But we need to go from 1 to 3.5. So here's my 0. So there's 1, 2, 3, and 4. So 3.5 is about right here. Okay, so then there's this. So I have my bracket here. And I know my 1 is right here. So I can pretty much leave it like that. I can draw this little line in here if I want to. I could do something along that lines here. And that's using brackets. The other way I can approach this is I can use a closed dot here and a closed dot there. And then I can connect my dot that way. So it just depends on how you want to look at it and how you want to do it, is how you're going to put it on your number line itself. So you just need to pay attention on how you want to represent that. Some people like open dot and closed dot. Some people like parentheses and brackets. So it's your choice on how you want to represent going from here all the way to there. Okay. So in this case, same thing. So I have parentheses here. So I know I'm going to start at negative infinity and I'm going to end at negative 1. And because I'm not going to include that negative 1, I'm going to have that and then I'm done. I'm going to take this information here. Now, when I plug it into here, because of the infinity symbol, I don't know what this is. So instead of using the infinity symbol, when I write this, I've got some random x value that does that. So when it's just an infinity by itself, just replace the infinity with an x, and then you wind up with that inequality, and then that goes into your set builder notation there. Now, we have x is less than negative 1. So since x is less than negative 1, then I'm going to come over here to my negative 1. And if you notice, if you always keep your variables on the left-hand side, this will tell you which way your arrow needs to go. So I can put an open dot right here at 1, and then I can shoot off into negative infinity. And so if you notice that this arrowhead here matches your greater than, or my less than sign here, they're going in the same direction. And so therefore, you know that you've done it correctly if you keep your variable on the left hand side. All right. So when we deal with inequalities and just trying to graph these notations and everything, sometimes we wind up with intersections and unions. So what we're going to do is we're going to graph each interval on the same number line. When we look at the intersection, what we're going to do, two colors is usually the best way of doing this. So, and I'll show you what I'm talking about when we get into this. You want to pick one color for one and then one color for the other oh, what am I thinking? The other interval notation piece. And then you want to see if they're intersecting, where they overlap. And where they overlap is where you're actually going to have your final answer. The union is where do they come together? So you want everything in common. And only that piece that are in common is what's going to count. So let's take a look at what I'm talking about here. So we have 1, 3, and then an intersection of 2, 6. So there's one, oops, put some color on this. 1, 2, 3, 4, 5, and 6 is what we're going to look at. So my first one, I want to color that one green. I'm going from a closed dot of 1 to a closed dot of 3. And then I'm intersecting, so I'm going to pick a different color, from 2 to 6. Oh, let me put a line from here to here. So from 2, I've got an open dot at 2, and I'm going to 6 with an open dot, and I'm doing that. So when it wants the final answer to this, then what you're going to have to do is you're going to have to look at where they overlap. And so if you notice, they are overlapping here and here. So that means when I write my final answer, open dots always win, just to let you know. Open dots always win. So when I write my final answer, I'm going to start at 2 and I'm going to end at 3, and I will include 3 because they both have a closed dot. Here at this 2, since one of them is an open dot and the other one's a closed dot, then the parenthesis wins because we don't actually include the number 2. All right. Let's try one more before I move on. So let's look at, let me see here. Let's go. I've got 1 and 3, and then I'm going to union a 2 and a 6. Okay. So let me come back over here real quick, and I'll do this. I want to copy that. And then I want to come over here and I want to paste it so I can have a number line to work with. So then I can lock it so I can play on it. All right, so here we go. So now we're going to look at our union. So we have 1, 2, 3, 4, 5, and 6. So when I'm taking a look at this, I want to look at everything that is going to be included in this. So on my first one, so I'm going to make this one red. So I'm going to start with an open dot here, and I'm going to run all the way to 3, and I'm going to close that there. And then I'm going to take this one here, and I've got an open dot here, and I'm going to run this all the way down here to 6. Now, here's where in a union, we kind of ignore things sometimes, because if you notice in my union, I've got that right there. I have an open dot in an actual included piece. When we are looking at a union, we include everything that's there, regardless if it's not here or if it is here. So since it is defined here at 2, when I do my union, I will include that. And so my union is going to include everything from here all the way to here. So when I write my answer, well, I'm including 1, and then I'm running all the way here to 6, but at 6 where I'm ending, I don't include that, and so I get a parenthesis. So when I'm unioning this, I'm looking at the whole, both of them together, and the only time that I worry about an open dot or a closed dot is if I have an endpoint that's out here by itself, like here at 6. Notice here at 1 I had a closed dot, and so therefore, excuse me, therefore I have a bracket here, but over here at 6 I have an open dot, and so then I have a parenthesis here. Unlike back here, where when I'm looking at their intersection, the open dot will always win on an intersection. In a union, it sometimes will and it sometimes won't. It just depends on where it's at. Okay. So now, let's look at the fun stuff. I like solving linear inequalities. Linear inequalities, when you're actually dealing with lines, is a bunch of fun. You're probably thinking, no, it's not, but it really is. All right, so linear inequalities in one variable. So basically we have an mx plus b situation, except instead of a equals 0, we have a greater than or less than situation that's happening here. So these are the 4 forms that we are going to be dealing with when we're talking about linear inequalities in one variable. And so the key thing is here is when you solve these equations, 99% of the problem is just like solving all your equations, linear equations, how you've done in the past. The only difference is this piece right here. When we get down to where you either multiply or divide, if you multiply or divide by a negative number, then your inequality sign will flip. Say it one more time. When you multiply or divide by a negative number, so that's if this, or that, if any of those are negative, when you do that division piece to get x by itself, if it's a negative number, you will flip that inequality sign. So let's look at a couple of these. Solve and graph the solution set on a number line. Okay. So what I want to do, I want to pretend that this is an equal sign and just solve this like normal. Don't go and try to do anything different. Just solve it like normal. Subtract a 2 from both sides. And so when I do that, I get a 3 over here. And then we're going to divide by a negative 3. And so I get x is equal to negative 1. But because I divided by a negative 3, so remember, this is a negative number. Since I am dividing by this negative 3 on both sides, that means my inequality sign here is going to be flipped. So this is what I am really looking at. And so this piece here is what I'm going to graph on my number line. So I'm going to actually graph x is greater than or equal to negative 1. Is that right? Yeah. So when I do that, I'm going to come over here to my negative 1. Again, I can use an open dot or a closed dot, or I can use a parenthesis or a bracket. It's your choice on how you want to do it. I like dots. I actually like dots a lot, especially the red ones. The red ones are really good dots. But anyway, again, my variables on the left-hand side, which is good. So this tells me I have a closed dot, and I'm going to run my arrow off pointing into that direction. And I'm done because I don't have anything else I'm bounded with. I'm just going to go off into infinity. If I'm going to do set builder notation, I would do it like negative 1, comma, and then write my infinity. That's what it looked like in interval notation. Okay. Inequality, interval. Let's see. Let's look at just making sure I got all the ones I want to do on this one. Yep. So when you're doing these, check to make sure that if you're not really sure if you've done it correctly, pick a number here, plug it back into the inequality sign, make sure it actually becomes a true inequality. Okay. Make sure the inequality is always true. So now let's look at another piece. Let's look at one more. Let's just give you one more. Let's go 3x plus 1. That is greater than 7x minus 15. All right, so take a few moments, solve this, write it in set builder notation and in interval notation as well. And let's just make sure that you understand before I move on to the next part of this, okay? So I'm going to give you a few moments to give you that opportunity to take care of this, and then we will pick back up. All right. So again, I always like to have, when I'm dealing with inequalities, my variables on the left-hand side. So I'm going to go ahead and subtract this 7x, and I wind up with negative 4x plus 1. And that's going to be greater than negative 15. I'm going to subtract the 1, so I get negative 4x is greater than negative 16. I'm going to divide through by negative 4. And then that means I'm going to flip my inequality sign, and then I wind up with a 4. So for set builder notation, I got my set of all x values such that x is less than 4. Or if I want it in interval notation, I'm going to go from 4 all the way to infinity. Okay. Oh, wait, I lied to you. We're not going positive infinity, are we? We're going negative infinity. So scratch that. I'm going from negative infinity because I want less than to 4. Here we go. All right. So now, what if we have fractions? So what if I have x plus 3 over 4 is greater than or equal to x minus 2, my goodness, x minus 2 over 3 plus 1 over 4. What happens if I give you a problem that looks like this? Remember when we solved these equations earlier and this was an equal sign? You're going to do the exact same thing. So I'm going to solve it doing this problem here. So 4 and a 4 will cancel. That leaves me with a 3x plus 3. That 3 and that 3 cancel, leave me with 4x minus 2. And that 4 will cancel, leave me with 3 times 1. And so now I'm going to just clean this up. I get 3x plus 9 is greater than or equal to 4x minus 8 plus 3. 3x plus 9 is greater than or equal to 4x minus 5. I'm going to move my 4 over here, so I get negative x plus 9 is greater than or equal to negative 5. Move the 9 over. Negative x is greater than or equal to negative 14. So that means my x is less than or equal to 14. So that means in set builder notation, all my x values such that x is less than or equal to 14. And then interval notation, since my x is less than, I'm going from negative infinity, but in this case, I'm actually going to include the 14. So I'm going to end it there. All right. Hopefully that wasn't too bad for you. So let's move on. So what happens if you get some really unusual answers? So let's take a look at this. Just like with equations, inequalities can also be inconsistent or all real numbers. So that's something you're going to have to take into consideration. So when we're doing this, if your inequalities, if your x variables cancel out and you have no more x variables at all whatsoever, and you wind up with a true statement, you're going to have all real numbers. But if all of your x's cancel out and you wind up with a false statement, you're going to have what's called no solution. So let's take a look at what I'm talking about. Here's your problem. So we're just going to solve this as normal. So I'm going to distribute my 3 here. So I get 3x plus 3. That's going to be greater than 3x plus 2. When I move my 3x's over, I cancel out my x's and I'm left with 3 is greater than 2. This is a true statement. So what that means is that if I'm looking at interval notation, I have all real numbers as an answer. If I'm looking at set builder notation, I can either write in the words or I can say x is all real numbers. However you want to do it. But either one will represent what you're saying here. So if my variables canceled out and this became a true statement, it's all real numbers. Unlike this one, when I move my x's over, they cancel out. I get a 1 is less than or equal to -1. That is not a true statement. So I either have the empty set or no solution. So those are the two different ways that you're going to see these, how they're going to be handled. So you're either going to have a true statement, which will generate all real numbers, or you're going to have a false statement, which will generate no solution. All right. So now let's look at the compound inequality. So you already know how to do these. The only difference is instead of doing once, because what we've normally had is we've had something that looks like this, or we've had something that looks like this. You now have a compound one. So what's going to happen is you're technically just going to do this twice. And so if you can keep it like this, and then you can just walk through the problem in this format here, and then you wind up with this. And so that's what, an 8. And then you can divide through by a 2. So then you wind up with -1 is less than or equal to x, which is less than 4. You can do that. That's absolutely okay. Or you can split it up and work the problem that way if it's simpler for you. So you want to make it simple for you. Don't worry about how all the examples may show it. It's what's going to be easier for you. And just remember to bring your answers back together in the very end, because you want to make sure that you want to keep everything together the best way. The only difference I would say here is I would leave the problems how they are. I would not put the x's on one side, because when you're finished, you have that. And so if you have the x is less, or I'm sorry, 1 is less than or equal to x, and then x is less than 4, when you put them back together, you will notice that it's just a lot easier and a lot cleaner just to bring them together in this format, because you're just sliding this is that piece, and then this is this piece with the negative sign. My fault. So again, you can do it in one big swoop like this, or you can do it in two separate parts. Now, once you have this done completely, so I've got -1 is less than or equal to x, which is less than 4. Now it's just coming over here and plotting it. So there's my -1, 2, I lied. 1, 2, 3, and 4. I've got a closed dot here. I've got an open dot here, and I'm going to connect them together. Or I have a bracket here and a parenthesis over here, and again, I'm going to put them together. So it's however or whatever makes better sense to you on how you want to graph these. Try it one more time. So take a few moments, try this problem, and see what you come up with. Don't worry about graphing it, but write it in interval notation form. So write this in interval notation form. So pause the video now. All right, welcome back. So I'm going to go ahead. I'm going to do it as one big problem. So I'm going to minus 1, and minus 1. And so we know that that's going to go away. So I get negative 4 is less than 2x is less than or equal to 2. I'm going to divide through by my 2. So I get negative 2 is less than x is less than or equal to 1. So in my interval notation, I have an open parentheses, negative 2, and I'm going to close it off at 1. All right. So hopefully there's no questions on that, and that makes pretty decent sense. Oh, wait. I lied to you, didn't I? It's not that one. It is a bracket. My bad. Sorry about that. It is a bracket because it's less than or equal to. I even said that, didn't I? Sorry. All right. So pick the way that you want to do it, or pay attention to how the directions tell you how to do it. If it doesn't tell you, then you get to pick. So hopefully those make sense to you. If you want to see it graphed on a number line, the same thing, negative 1, negative 2, and then 1. So we have an open dot here and a closed dot here, and that's what we got. Got a bracket here and a parenthesis here, and that's what we're looking at. You don't have to do both, one or the other. All right, so linear inequalities are pretty simple. Not much you have to do. You just have to remember if you ever divide by a negative that you are flipping those signs. Sorry. If you ever get a problem, let's go 9 less than or equal to negative 3x less than 15. If you ever get this and you have to divide through by the negative, make sure that you have a true statement, because sometimes when you divide through by these negatives, sometimes it comes off to be a false statement, and then you wind up with having to separate this stuff out, because I've got negative 3 is greater than or equal to x, and then I have x is greater than or equal to negative 5. And so if negative 3 is greater than x, but it's also greater than or equal to 5, I have this really weird wonky way. And so you have an either or on this piece here. What's missing here is not all the numbers are going to work. And typically you don't see the compound inequalities that have this negative sign here in the middle. So if you see this piece here, just go back and check your work to make sure everything is okay. But typically you won't see problems like this in a compound inequality form. The only way you'll see those is if they're separated or not. All right. So then let's move on. Absolute value inequalities. These ones are a little tricky, so you have to pay attention. So this is probably new to a lot of you. So I'm going to go a little slow here so you understand exactly what we're looking at. So in an absolute value, you have two specific ways that you have to write it. If your absolute value is ever less than the other side, so we're focusing on less than the other side, this is how you rewrite it so you can solve it. So you rewrite it as a compound inequality. If it's ever greater than, then you have to separate it. So that means when you graph this, these are not going to overlap. You're actually going to have two separate, what am I thinking? Two separate graphs on your number line, and you're going to have a space in between where there are not true statements. And you see these in absolute values. So we're going to look at both of these here. So let's take a look. So I don't like having my absolute value on the right hand side. So that's just a personal preference. So what I would do, and that's why I just switched it to here. It's the same question as before. I just switched it so I have more room to write. Is I'm just going to rewrite this over here so you can see, because I personally like having my stuff like this. That way I can see specifically what's going on. And so now that I'm sitting here, I know I've got the greater than. So if I go back to my earlier piece, number 2 here, number 2 says greater than. So I've got 2 specific things I got to look at here. So I'm going to look at, sorry, I'm going to look at when the right side is going to be negative, and I'm going to just look at it the way it's written. So I'm going to take this, I'm going to look at it the way it's written. So I'm going to look at it like that. And then I'm going to look at it when the other side is negative. But when I do that, I'm going to flip that sign. And this is what we call an OR situation. Because the absolute value we're talking about greater than, we have an OR situation. So I'm going to solve this normally. So I get negative 3x is greater than, what is that, 12? Divide through by the negative 3. And I get x is less than negative 4. And then over here, I get negative 3x. I'm going to move the 6 over. And that gets me negative 24. Divide through by the 3, and I get x is greater than 8. So see, I have these 2 things. And if you think about it, I got one running off into negative infinity in that direction and one running off into positive infinity in that direction. So when I actually look at graphing this on here, 2, 4, 6, 8. I don't know if I have enough. Yeah, I do. 2, 4, 6, 8, 2, negative 4, negative 6, negative 8. X is less than negative 4. So x is less than negative 4. So I'm going to go off into that direction. And I got x is greater than 8. And so I'm going to go off into that direction. So when I write my interval notation, I go negative infinity up to negative 4, union 8 to positive infinity. And you notice I've got this big section over here where all these answers here in the middle do not make this a true statement. So that's why I have this big, huge gap in the middle, because it's only true for where I drew my picture at. So when you have this format here, you are going to have a gap. There are going to be pieces where it's only true when this part or this part's going to happen. And that's why there's an OR. So when you see an OR, know that you're going to have a union, and know that you're going to have a gap. Okay? Let's try again. This case, this is x, the absolute value of x minus 2 is less than negative 5, or less than 5. So I told you if you're ever less than, so this is my c value over here on this side. So when I rewrite this, I go negative 5 is less than x minus 2, which is less than 5. I rewrite it like this. Solve it like we did earlier. So I'm going to add 2 everywhere. And so I wind up with negative 3 less than x less than 7. So my interval notation for this one would be a parenthesis, negative 3 to 7. And then I'm done. Okay. So what was it? So 2, 4, 6, and 8, negative, 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 2, 4, 6, 8. So here's my negative 3 here. There's my 7 here. And I want everything in between. All right. I think, yep, that is it. So when you are dealing with these, just pay attention. The absolute value is the only one that really has rules. So if your absolute value is less than the number, then you write it as a compound inequality. And if your absolute value is greater than your number, you're going to split it up and have an OR situation. And so that means you're going to have on your number line, you're going to have a big gap in between. It may not be big, it could be small, but you're going to have a gap in between your number lines. So you're going to have something going off into negative infinity and something going off into positive infinity. Okay. I hope this wasn't too painful or anything. So if you have any questions, please make sure you're emailing me, sending me remind questions. Make sure you utilize the Ask the Instructor button on the homework. This concludes linear and absolute value inequalities. And this is also the final topic before your first test. So that'd be October 2nd. So please make sure when you go through there that you are, keeping up with your homework and that you are looking at the reviews as well. And I hope everything's going well. So if there is nothing else, which there's not because I'm in a room by myself, I guess I am done. So I will talk to you soon. TTFN. Ta-ta for now.